we can graph the energetic pathway of a chemical reaction through a chart like this. This is a very common way of looking at the actual energetic exchange that is happening between reactants and products. So we have a graph here where the x-axis is the progress of the reaction over time. We're not so concerned about that aspect as much as the y-axis of this chart, which is showing the energy of the chemical system in terms of kilojoules per mole, which is the most common way that we tend to quantify the energy of a chemical reaction. Joules are such a small unit that this is a more appropriate scale for us. Once again, we're looking at this in terms quantitatively of energy on a mole level rather than a mass level. So what we have is the pathway of the progress of a chemical reaction here, and actually two alternatives. So let's say that we have reactants A, B, and we're hoping to have a reaction that produces product C, D. There's always going to be some sort of energy investment to break the bonds of A and B so that the formation of bonds C and D can actually happen. In this case, we have an exothermic reaction where the amount of energy before the reaction in the system is higher than the energy of the products. We now have on this side of the chart a more stable chemical system, lower entropy, and this is pretty much what matter seeks to do unless we provide external energy to where we would actually have higher energy in the products than the reactants. That would be endothermic, and that is inherently less stable. So as the reaction progresses, the amount of internal energy that is in the system at being supplied by heat ultimately, or whatever energy is available, it could be electrical or what have you, has to be sufficient enough to actually break the bonds of the reactants. And the point where the bonds are being broken so new ones can be formed is the high point of our energy graph here, and this is called the activated complex. So reactions don't happen under particular conditions if there isn't sufficient activation energy to make that happen, and that's what a Gibbs analysis helps do it, and other thermodynamic analyses do for a chemical reaction at a certain temperature. So in this case, we're assuming that there was sufficient energy at the conditions this reaction took place, and bonds were formed after these bonds were broken, and we have our products. And we will also note here is that the difference, the change in the energy of the system, that's our change in enthalpy, that's our delta H. And so that difference of the beginning on this graph going from left to right, that's our change in enthalpy. So this essentially is the difference between the bonds broken of the reactants to the bonds formed of the product. So we can display our change in enthalpy this way. Now, this is what is going to happen if we don't have some means of lowering the activation energy, and there are many reactions that will not take place under the conditions they're in unless there is something else to help that reaction happen by lowering the activation energy, and that is often a catalyst. So a catalyst can be lots of things. We tend to think of in biological systems enzymes as catalysts, and as you learn in biology, They act as sort of a host for the reaction to take place and make it more energetically favorable without the enzyme becoming part of the actual reaction. Our body makes enzymes like lactase to digest lactose, milk sugar, or amylase to digest starches, start breaking those down into simple sugars and so forth. But the fundamental thing that any type of catalyst does, whether it's biological or it's not biological, like say platinum, that's a very common metallic catalyst for helping lower the activation energy. We can take a look at a graph like this that shows the uncatalyzed higher energy requirement and the catalyzed lower energy requirement. And of course, we can measure that difference between the two, and we can answer the question, how much less energy is needed with a catalyst? And so it shows the energetic advantages of having a catalyst to make this reaction happen. So the activation energy, in closing, is the energy required to make a chemical reaction happen by breaking the bonds of the reactants so that new bonds can be formed. And in the case of these typical exothermic reactions, we have a lower energy state at the end and what would be a negative change in enthalpy in this case, because the energy of the system has declined.